Good evening, everybody. My name is Marek Kubicki. I'm professor of psychiatry and radiology at Harvard Medical School. I'm also one of the directors of psychiatry neuroimaging laboratory at Brigham and Women's Hospital, Harvard Medical School. I'm honored to be part of the symposium. Thank you, organizers, for inviting us, for giving us the opportunity to present. Thank you, the audience, for listening to this live as well as later on to our recording. And as part of the symposium, my presentation is the first one, and I will try to introduce to you the issue of white matter pathology in schizophrenia. Why is it so important to look at it? What are the tools that we have to measure in vivo using neuroimaging pathology in white matter in schizophrenia? How are we going about it? And what are the still roadblocks and limitations to our research? And my talk will be followed by Suhaila, Amanda, and Johanna's talks that would expand on how in our laboratory we are dealing with those roadblocks and what is our most recent research in this regard. As most of you already know, schizophrenia is a chronic disorder that affects just under 1% of the world's population. The onset of symptoms is in late adolescence or early adulthood. It was termed dementia precox by Emil Kraepelin a long time ago, which means accelerated aging. It has a clear genetic risk. It is a developmental disorder but shows progression. And finally, despite years of research, the anatomical, cellular, and molecular basis of schizophrenia remain elusive. I've been doing white matter research in schizophrenia for over 20 years, and what drew me to this research is the clear and overwhelming evidence that there is something wrong in the way the brain is wired in schizophrenia. Especially connections between frontal and temporal lobes are definitely affected. And it has been proposed by Wernicke and has been demonstrated very elegantly by Carl Friston and Daniel Weinberger, amongst the others. That's either clinical or functional and structural studies, neuroimaging studies, so this is indirect evidence. However, there is also direct evidence that looks at myelin abnormalities, and myelin is the structure that surrounds axons and is major component of white matter in the brain, and those myelin sheets show abnormalities in postmortem and DNA analysis. It is important to look at white matter for many reasons, and one of those reasons is because the onset of psychosis falls around the time when white matter maturational trajectory reaches its peak. And as you can see, gray matter peaks earlier, but white matter peaks around the onset of psychosis. And if there's something wrong with the way white matter maturates around here, it will obviously affect the clinical and cognitive symptoms and maybe even cause the conversion to psychosis. Obviously, there are several different scenarios that could give us the appearance of accelerated aging, and that's important because what we are measuring is really the effect here, around here, whether we're looking at first episode or chronic or more chronic data sets. We're really comparing the differences between groups. And those differences could be caused by either shift of this trajectory and peak earlier, or later to that matter, whether it could be caused by pathology around the onset of psychosis and appearance of accelerated aging, or whether it could start happening around the onset of psychosis and it could keep affecting white matter from the onset of psychosis to the later ages. These measures or these trajectories are important to investigate. However, until recently, we didn't really have the tools to do that. The major tools that we have to look at in vivo brain structure of white matter are neuroimaging tools. And one of them is structural neuroimaging. This is the example of T1 weighted image showing clear difference in contrast between gray matter, white matter, and CSF. Once these three compartments are separated, the white matter volume can be measured and then statistically compared between controls and patients with schizophrenia. But we are not interested in macrostructure as much as we are interested in microstructure. And in 1994, looking at microstructure of white matter has become possible by invention of diffusion tensor imaging. Diffusion tensor imaging, or DTI, has been proposed as a tool to explore white matter microstructural abnormalities, not only in schizophrenia, but in any other diseases. And the way it works is that we are measuring water diffusion at each of those points in the brain. We're sampling in many different directions, and we're deriving this shape of the water diffusion in this ellipsoid called tensor. This tensor has its predominant direction, which is used to do so-called diffusion tractography. But the shape can be also estimated with something that we call fractional anisotropy. It's a scalar measure. It's the most popular measure that defines whether there's something wrong with white matter or not. This fractional anisotropy is very sensitive to any pathology that affects white matter, but it's not specific to any of those. So either of those pathologies, whether it's axonal density, myelin, fiber crossings, expansion of extracellular space, or glial scars, they all affect fractional anisotropy in one way or the other. Once the fractional anisotropy is estimated for each of these ellipsoids, then it can be either averaged over the region of interest that is coming from the brain atlases of white matter of largest white matter bundles. It can be compared between groups on the voxel by voxel basis. This method is called TBSS, or tract-based spatial statistics. Can be compared based on tractography analysis. So for each individual tract, fractional anisotropy can be averaged and compared between groups. And connectivity can be also measured using connectomics, where we are looking at the statistical dependence of one region on the other. All these methods have been obviously employed in schizophrenia because DTI has been around for over 20 years. And the results overwhelmingly show that there's something wrong with white matter as measured with DTI and fractional anisotropy in patients when compared to controls. There's obviously a difference. It is still not clear, however, where is the difference and what time of schizophrenia the difference is most abundant, most highest. Each of those dots, we've done this experiment in 2011, but it's also very much true nowadays. It's going to be just many more points, but each point represents a result of a study. And as you can see, there's no difference between first episodes or chronics in the distribution of those points. But there's no clear pattern of findings either. Meaning that it's not like all the studies showing the pathology in the same location. The locations are all over the white matter. And there's obviously many reasons that we cannot say more about what is wrong with schizophrenia. And some of those reasons are listed here. Obviously, the longitudinal studies using neuroimaging are difficult to perform because imaging is expensive and because it is very difficult to keep subjects in study for a long period of time. Fractional isotropy, as I said, is sensitive but not very specific biologically. Excuse me. That means that we're not really sure what biologically happens to affect our imaging findings. Because neuroimaging is expensive, we have limited power and small sample sizes. And none of those additional factors are taken into account, mostly because the samples are small and some of this data is not recorded. There are some studies that are starting to tackle the issues of accelerated aging, for example, in a larger cohorts, and coming up with these modeling of white matter in comparison subjects in patients with schizophrenia, clearly showing that there's something wrong with happening with age in white matter. There are also attempts to identify what exactly is wrong with white matter. There's abnormalities. There are abnormalities pointing to myelin. There are also abnormalities pointing to neuroinflammation. And how those two pathologies are related to each other, and how to separate them, to differentiate them, and to measure them separately along the schizophrenia trajectory is the matter of active research. There are also a bunch of worldwide collaborative efforts in DTI research that are leading to increase the sample size and the power of the analysis, and make it possible to investigate all those covariates that we listed as the limitations of in our field. There are obviously the enigma everybody heard about, that this is being led by Paul Thompson. It's a big effort of combining DTI with genetic and clinical data. Another genetic and DTI data combination is being led in a Genius consortium. This Naples consortium, which collects diffusion data before the onset of psychosis in individuals at risk to develop psychosis. There's also big collaborative efforts in Australia and in UK, amongst the others. And this is basically it. We in 3 next presentations, we're gonna show you how we are tackling those issues and how we are attempting to increase our knowledge about what pathologies and how white matter pathologies affect schizophrenia spectrum along the age continuum. This is the end of my presentation. I wanted to thank my collaborators that are especially helping with neuroimaging, Ofer Pasternak, Yogesh, Rati, Suhaila, Amanda, and Johanna, who you will be hearing from more about what they're doing. There are also clinical collaborators who helped me to collect the large data that will be showing you the results of the analysis on, and this is the finding that helped me to perform the research that we're presenting today. So thank you.